Hi, and welcome to module number 51. In this module, we're going to discuss dimensionality reduction. And we're going to begin by asking, what is dimensionality reduction? So in machine learning and statistics, dimensionality reduction or dimension reduction is the process of reducing the number of random variables under consideration via obtaining a set of principal variables. It can be divided into feature selection and feature extraction. Now, specifically, we're going to look at two different styles here. Two different styles of dimensionality reduction. The first will be principal component analysis, or PCA, and the second will be random projections. In a nutshell, in PCA, you project your data onto a pre-computed set of vectors that set of vectors offers good energy compaction, and we'll chat in a moment about how this is similar but not identical to a sparsifying matrix. And in the random projections, you're projecting onto noise. So these are two different types of projections. The first one, a fine-tuned projection. The second one, a random one. And both of them can be used to reduce the dimensionality of the data. And reducing the dimensionality of the data has the benefit of, for example, lower computation. So first, principal component analysis, which is also called PCA. In PCA, we typically have a point cloud of data. Here we have data in 2D, and we can apply a transformation. And what you're seeing here is that overall, the point cloud of data seems to be located in this oval. And this line, this diagonal line, is the first dimension of the PCA. And in PCA, the style is that the first dimension will have the most energy, the second one, the second most energy, and so on. So much of the energy in these points can be characterized by a coefficient along this first dimension. And if the energy that's not in that first dimension is arranged around this second direction, the second PCA dimension, which is orthogonal to the first one. And it's clear from the sketch that the second dimension typically has lower coefficients. So overall, we want a transformation that arranges most of the variance in the point cloud along a small number of directions. And we might even be able to throw away dimensions with a small amount of information, dimensions that the large majority of the time those coefficients are near zero. So we're soon going to compute this transform, but I just wanted to begin with the idea. The idea is identify the coefficients along directions that have much of the energy. Okay, so this does seem similar to a sparsifying transform, but let's contrast it to a sparsifying transform. The similarity is that there's energy compaction. In the sparsifying transform case, we know that the signal is sparse. We don't necessarily know where the large coefficients are. Possibly in an image, we know that the low frequency wavelet coefficients will often contain much of the energy. But in other applications for other types of signals, we may not know much, if anything, about where the large coefficients are. And therefore, intuitively, the emphasis is, given the support set, given the locations of the large ones, we know that it's very sparse. In PCA, we know statistically where the large coefficients are. So we don't necessarily know exactly, but we have a feel where they are. And so the emphasis is on, we know where they are, and given where they are, it's quite sparse, maybe not very sparse. So what's a possible application of this? That could be, one example would be identifying digits. Imagine that you're the post office and you have hundreds of letters or packages or postcards an hour that go through your system. And one possibility is to have a person who looks through each of these and keys in the zip code. But of course, number one, it would be costly to have people at all the post offices doing this sort of thing. And second of all, putting aside the cost, this would just be a pretty boring job. So ideally, we'd like to have a computer perform this in an automated way. So we're going to be applying PCA to each different digit. Each different digit will have a bunch of principal components, perhaps m principal components, U1 through UM, and we're going to be multiplying the data by the principal components. What that really means is our data is going to be a grid of pixels, okay, a square, or perhaps a rectangle, and you take this 2D grid of pixels and you convert it to a vector, and then you multiply this vector by a matrix. Each of the rows of the matrix is one of the principal components, U1, U2, up to U capital N. We then have capital N coefficients. If these numbers overall tend to be large, especially the lower numbers, again, the lower numbers contain the most energy on average. If they're large, then that digit probably appeared. On the other hand, if they're small, if the coefficients are small, it's unlikely that that digit was there. So this is a form of hypothesis testing. We've taken the high dimensional space, these pixels, perhaps we have a 16 by 16 grid of pixels, and this is 256 dimensional. And maybe we boil it down to 5 dimensions. And now a hypothesis testing problem in 5 dimensions is much simpler than before. So having discussed the applications and the big idea, we want to understand how to perform PCA. We want a good projection. So we begin with a point cloud. Our point cloud is comprised of n vectors, and each of them is d-dimensional. So xn, where the index n is between 1 and capital N, is in Rd. Again, we want the best projection vector. We denote it by u1, and it packs as much average energy as possible. So we want to analyze the expectation and the variance of the coefficient. The coefficient is u1 transpose x. So first of all, the expected value. The expected value of the coefficient, the expected of u1 transpose x, is, because of linearity of expectation, it's equal to u1 transpose multiplied by e of x. Now again, x is a vector. u1 transpose is a row vector because u1 is a column vector. And row times column is an inner product, which gives us a scalar. And the average value of that scalar is u1 transpose times the expected value of the random vector x. Now the variance. The variance of the coefficient is the variance of u1 transpose x, which again is a scalar. And this is the expected value of the difference between the coefficient and its expected, which we just calculated. And we square that difference and take the expectation. So the expected squared difference. Now, it can be shown that the variance of u1 transpose x is equal to u1 transpose times the covariance matrix of the data times u1. The covariance of matrix of the data is denoted by S, and it's equal to the expected value of essentially XX transpose. Now recall, X is again a column, X transpose is a row, and therefore XX transpose is a matrix. So I slightly missed the term here, and that was on purpose. You can implicitly assume that this is that X is zero mean. If it's not zero mean, you can subtract it off. If you don't want to do that, you can just perform these adjustments in the computation. So if we denote X tilde by X minus E of X, then the covariance matrix is the expected value of X tilde times X tilde transpose. So that's one aspect that I want to highlight. Another aspect that I want to highlight, this is a covariance matrix. It's not a covariance scalar, it's not a covariance vector. For every two indices, n1 and n2, we want the covariance between the two indices. That's why we need a matrix. Okay, so we now have the expected value of the coefficient and the variance of the coefficient. Let's continue. Again, what we primarily want is the biggest energy in U1. So we want the variance of that coefficient. The coefficient again is U1 transpose X. We want it to be as large as possible. And recall that the variance of that coefficient is U1 transpose S U1. We add a constraint that U1, its L2 norm is equal to 1. So this is unit norm and L2 norm, to be clear. So the L2 norm of U1. How do we solve this? We maximize the variance of the coefficient, which is equal to U1 transpose S U1, plus lambda times 1 minus U1 transpose U1. Now, what's this new term? U1 is a vector. U1 transpose is a row. Their product is, well, it's an inner product. It gives us a scalar. That scalar is equal to an inner product between U1 itself, which is equal to the squared L2 norm of U1. So we want the L2 norm to be equal to 1, which means that we want the squared L2 norm to be equals to 1. And now look at this Lagrangian parameter lambda. If lambda is large, it'll force that 1 minus the squared L2 norm will be small, meaning that the squared L2 norm will be close to 1. So we push the Lagrangian to be rather large, and then that forces U1 to have the appropriate L2 norm. And then the variance, the maximal variance U1 pops out. Now, it can be shown that a solution of this maximization satisfies the covariance matrix times S multiplied by U1 is equal to lambda 1 times U1, where lambda 1 is an eigenvalue of the covariance matrix S. Additionally, U1 is an eigenvector of the covariance matrix S. So we're saying that U1 is a eigenvector of S, and not only that, it's the eigenvector that corresponds to the most energy. And how much energy is that? U1 transpose SU1, again, that's the variance of the coefficient. That's equal to, well, U1 transpose times, well, S times U1 is equal to, as we just discussed, lambda 1 times U1. So we have U1 transpose multiplied by lambda 1 U1. U1 transpose times U1 is, as we discussed, equal to 1, and we're left with lambda 1. So the largest eigenvalue of the covariance matrix S gives us the amount of energy. Overall, an optimal n-dimensional projection corresponds to m eigenvectors, and these m eigenvectors correspond to the largest eigenvalues. Okay, so we now understand how to perform PCA. As I said, there's another element to dimensionality reduction, and that element is random projections. This will be the last portion of the course. Well, why random? Sometimes we know a sparsifying matrix, other times we don't. Sometimes we have data to calculate the principal components, PCA, sometimes we don't. Another problem is that PCA often suffers from outliers. PCA has other problems. So sometimes random projections may be advantageous with respect to PCA. So what we do, we compute m random projections of the data, where m is typically quite a bit smaller than the true underlying dimensionality d of the data. And on average, especially in high dimensions, random projections are approximately energy preserving, and they approximately preserve the geometric structure of the space. And surprisingly, they're clearly not optimal in terms of energy compaction, but they're often not far from optimal. So when we cannot do PCA, what we do instead, we perform random projections, and then we perform hypothesis testing on the random projections. So that'll be it for this module, and that's the last module of the semester. Thanks.